There is a limit to how far back in time we were ever supposed to see. For centuries, the night sky functioned like a curtain, hiding the beginning of everything behind a veil of distance and darkness. We believed that with better telescopes, sharper mirrors, and more powerful instruments, the universe would slowly reveal its history in neat and predictable layers. Each generation of scientists pushed a little further, expecting clarity. Instead, what they found was confusion. When the James Webb Space Telescope unfolded its gold-plated mirror 1,000,000 miles from Earth and turned its gaze toward the faintest, reddest smudges of light in the cosmos, it was designed to confirm our best models of cosmic history. It was built to look back over 13 billion years, to the era when the first galaxies ignited out of darkness. It was meant to validate the timeline written in textbooks, to refine our understanding of how stars formed, how matter gathered, how structure emerged from chaos. But when Webb looked too deep into space, it did not simply show us baby galaxies forming gently in a young universe. It revealed structures that appeared too large, too massive, too mature for their age. It detected patterns that did not fit comfortably inside our most trusted cosmological frameworks. It found galaxies that seemed to have grown up too quickly, black holes that had no clear origin story, and hints that the early universe may not have unfolded the way we thought. Light that began its journey billions of years before Earth even existed has now reached us, stretched and reddened by cosmic expansion. Embedded in that ancient light are messages from a time when the universe was only a few 100 million years old. What Webb uncovered in that faint infrared glow has forced astronomers to confront a possibility both exhilarating and unsettling. Our cosmic timeline might be incomplete. The terrifying part is not that the universe is violent or dark. We have known that for decades. The terrifying part is that the foundations of our cosmic story may require revision. When the deepest images ever taken were processed and analyzed, they did not simply add detail to the known picture. They hinted that something about our assumptions, about galaxy formation, about the growth of structure, perhaps even about dark matter itself, might be missing. For the first time, we are staring directly at the dawn of galaxies, and what stares back is not entirely what we expected. If you are drawn to the deepest questions about the universe and the mysteries hidden in its earliest light, subscribe to The Boring Universe and join this journey. Like this video to support long-form science storytelling, and share your thoughts in the comments below. And tell us, which part of the country are you watching from? The James Webb Space Telescope did not begin as a simple successor to Hubble. It began as a response to a profound limitation. The Hubble Space Telescope had transformed astronomy by delivering images of extraordinary clarity in visible and ultraviolet light. It revealed star-forming regions in exquisite detail and captured the iconic deep-field images that showed thousands of galaxies in a patch of sky no larger than a grain of sand held at arm's length. Yet even Hubble had boundaries imposed by physics itself. As the universe expands, light traveling across cosmic distances is stretched. This process, known as cosmological redshift, shifts light from shorter wavelengths toward longer ones. The more distant a galaxy is, the faster it recedes from us due to cosmic expansion, and the more its light is stretched. By the time light from the earliest galaxies reaches Earth, it is no longer visible in optical wavelengths. It has been pulled deep into the infrared. Hubble could see far, but it could not see far enough in the infrared to study the very first generation of galaxies. To truly observe the cosmic dawn, the period when the first stars ignited and galaxies assembled, astronomers needed a telescope optimized for infrared sensitivity, one capable of operating at extremely low temperatures to avoid drowning in its own thermal glow. James Webb was engineered for this purpose. Its primary mirror spanned 6.5 meters, composed of 18 hexagonal segments coated in gold to maximize infrared reflectivity. Gold, unlike silver or aluminum, reflects infrared light with remarkable efficiency. Each segment had to unfold and align in space with nanometer precision, forming a single smooth optical surface larger than any ever deployed beyond Earth's atmosphere. To detect the faintest infrared photons from galaxies over 13 billion light-years away, Webb must remain cold, extremely cold. Its 5-layer sunshield, roughly the size of a tennis court, blocks radiation from the Sun, Earth, and Moon, allowing the telescope to cool to temperatures below -220 degrees Celsius. Only under such conditions can its instruments detect the whisper of ancient light without interference. Webb does not orbit Earth like Hubble. Instead, it resides near the second Lagrange point. known as L2, about 1.5 million kilometers away. At this gravitationally balanced location, the telescope can maintain a stable orientation with its sunshield permanently facing the Sun and Earth, ensuring continuous darkness and thermal stability. This position also allows uninterrupted observation of deep space, free from the frequent eclipses that would disrupt data collection in low Earth orbit. The primary scientific mission of James Webb was ambitious yet clear. It aimed to study four major themes: the first, light and reionization; the assembly of galaxies; the birth of stars and planetary systems; and the origins of planetary systems capable of supporting life. Of these, the most fundamental was the first, light, the epoch when the universe transitioned from darkness to illumination. After the Big Bang, the universe was hot, dense, and opaque. As it expanded and cooled, protons and electrons combined to form neutral hydrogen in a process known as recombination, around 380,000 years after the beginning. At that moment, light was able to travel freely for the first time, leaving behind what we now observe as the cosmic microwave background. But after recombination, the universe entered a period often referred to as the cosmic dark ages. There were no stars yet, no galaxies, only vast clouds of neutral hydrogen slowly responding to gravitational perturbations seeded by quantum fluctuations in the early universe. Over time, gravity amplified tiny density variations. Regions slightly denser than average attracted more matter, growing progressively heavier. Within these collapsing halos, gas cooled and condensed, eventually igniting the first stars. These early stars were likely massive, short-lived, and composed almost entirely of hydrogen and helium, the only elements forged in significant quantities during the first minutes after the Big Bang. As these first stars formed and emitted intense ultraviolet radiation, they began to reionize the surrounding hydrogen, transforming the neutral intergalactic medium into an ionized plasma once again. This epoch of reionization marked a profound shift in cosmic history. Galaxies were assembling, stars were forming in increasing numbers, and the large-scale structure of the universe was taking shape. For decades, astronomers relied on indirect evidence and theoretical modeling to reconstruct this era. Computer simulations based on the Lambda cold dark matter model, our standard cosmological framework, predicted how matter should clump and evolve. According to this model, dark matter provides the gravitational scaffolding for galaxy formation. Baryonic matter, the ordinary matter made of protons and neutrons, falls into dark matter halos, cools, and forms stars. In this picture, structure grows hierarchically. Small objects form first, merging over time into larger galaxies. The earliest galaxies should be relatively small and irregular. Massive, well-structured galaxies, comparable to the Milky Way, were not expected to exist until billions of years later. James Webb was tasked with testing these predictions directly. By observing galaxies at redshifts greater than 10, corresponding to times less than 500 million years after the Big Bang, astronomers hoped to witness the earliest phases of galactic assembly. The expectation was clear: primitive, faint systems, gradually building complexity over time. When the first deep-field images from Webb were released, the scientific community reacted with astonishment. The clarity and depth surpassed anything previously achieved. Galaxies appeared at staggering distances, their light so redshifted that only Webb could capture them. Spectroscopic measurements began to confirm extreme redshifts, placing some of these objects within the first few 100 million years of cosmic history. But alongside the triumph came unease. Some of these early galaxies appeared far more massive than models predicted. Their brightness implied significant stellar populations already in place. In other words, they had formed stars rapidly and efficiently in a universe that was barely out of infancy. Estimating the mass of a distant galaxy is not straightforward. Astronomers infer stellar mass from luminosity, corrected for redshift and dust absorption, using population synthesis models that estimate how much light different types of stars produce. When these calculations were applied to certain high, redshift candidates observed by Webb, the implied stellar masses approached billions of solar masses at times when the universe was less than 500 million years old. According to conventional hierarchical formation models, assembling that much stellar mass so quickly would require either extraordinarily efficient star formation or a revision of how dark matter halos grow and merge in the early universe. Some initial mass estimates were later revised downward as spectroscopic data refined redshift measurements. But the pattern persisted. The early universe seemed to be more productive than anticipated. Another surprise emerged from the morphology of these distant systems. Rather than being uniformly chaotic and amorphous, some appeared surprisingly structured. While resolution limits make detailed classification challenging, hints of disk-like features and organized star formation were observed at redshifts where such maturity was not expected. The existence of supermassive black holes in the early universe further complicates the picture. Even before Webb, quasars had been detected at redshifts above 7, indicating that black holes with masses of 1 billion suns existed less than 1 billion years after the Big Bang. The formation of such massive objects in such a short time poses a long-standing puzzle. Webb's infrared capabilities now allow astronomers to probe even earlier epochs, searching for the seeds of these black holes. If early galaxies were forming stars rapidly and potentially hosting growing black holes, then the timeline of structure formation might need adjustment. One possibility is that star formation in the early universe was more efficient than current models assume. Another is that the initial mass function of the first stars favored extremely massive stars, which would evolve quickly and contribute to rapid chemical enrichment and black hole formation. It is important to distinguish between anomalies and revolutions. The Lambda cold dark matter model has been extraordinarily successful in explaining large-scale cosmic structure, the anisotropies of the cosmic microwave background, and the distribution of galaxies across billions of light years. A few surprising observations do not automatically invalidate it. However, when multiple lines of evidence converge on similar tensions, scientists begin to scrutinize underlying assumptions. Webb's early data suggest that galaxy assembly may have progressed faster than predicted in certain environments. This does not necessarily imply that our cosmological model is wrong, but it may indicate that baryonic physics, how gas cools, forms stars, and interacts with radiation, needs refinement. Simulations rely on subgrid models to represent complex processes like supernova feedback and radiative transfer. Small changes in these prescriptions can produce significant differences in predicted galaxy growth. There is also the question of observational bias. The earliest Webb surveys target limited patches of sky. It is possible that the most massive early galaxies are overrepresented in these fields, giving an impression of abundance that may not reflect the broader cosmos. As larger and deeper surveys accumulate, statistical samples will improve, clarifying whether these objects are rare outliers or representative of a broader trend. Yet even cautious interpretation cannot diminish the profound significance of directly observing galaxies from the first few 100 million years of cosmic history. For the first time, we are not inferring their existence indirectly through theoretical extrapolation. We are measuring their spectra, estimating their chemical compositions, and mapping their distribution. One of Webb's key instruments, the near-infrared spectrograph, allows astronomers to decompose incoming light into its constituent wavelengths. By identifying emission and absorption lines, scientists can determine redshifts precisely and detect the presence of elements such as oxygen, carbon, and nitrogen. The detection of these heavier elements in early galaxies indicates that at least one generation of stars had already formed and died, enriching the interstellar medium. Chemical enrichment so early suggests rapid stellar evolution cycles. Massive stars live only millions of years before exploding as supernovae, dispersing heavier elements into surrounding gas. If such processes were widespread within a few 100 million years, then star formation must commence very soon after the cosmic dark ages ended. The timeline is compressing. The gap between recombination and the emergence of complex, chemically enriched galaxies appears narrower than once believed. The universe may have transitioned from simplicity to structure with startling speed. This acceleration challenges not only our models of galaxy formation but our intuitive sense of cosmic time. We often imagine the early universe as slow, gradual, and primitive. Webb's observations suggest dynamism, efficiency, and rapid organization. None of this implies catastrophe. The terrifying aspect lies in the epistemological shift. For decades, cosmology has operated within a framework that seems stable and predictive. Now, with unprecedented observational power, we are discovering that some of our expectations about the earliest epochs may have been too conservative. Science advances not through comfort, but through tension between theory and observation. The James Webb Space Telescope was built to illuminate the cosmic dawn. In doing so, it has revealed a universe that may have grown up faster than we imagined, assembling complexity in a fraction of the time our models allowed. As more data arrives, as spectra are refined and surveys expand, We may find that these early surprises integrate smoothly into an updated cosmological narrative. Or we may uncover deeper inconsistencies that point toward new physics, new mechanisms, or even revisions to the nature of dark matter itself. For now, what Webb has found is not a definitive overthrow of cosmology, but a series of luminous questions written in ancient light. And those questions reach back to the very beginning, forcing us to confront the possibility that the story of how the universe built its first galaxies is more dramatic and more mysterious than we ever anticipated. When astronomers first began analyzing the deepest infrared images from the James Webb Space Telescope, the initial reaction was excitement. The data were pristine. The redshift estimates were extraordinary. The faint smudges of light that had once been barely detectable now appeared with structure and clarity. But as teams around the world processed photometric measurements and ran spectral confirmations, a more unsettling pattern began to emerge. Some of the galaxies Webb detected at extreme redshifts appeared too bright. Brightness in astronomy is not merely a visual property. At cosmological distances, brightness becomes a proxy for stellar mass and star formation rate. When a galaxy shines intensely in the infrared at a redshift corresponding to only 300 or 400 million years after the Big Bang, it implies that a significant population of stars has already formed and matured. The early universe, according to our standard cosmological framework, should not have had enough time to assemble such massive systems. The prevailing model of cosmic evolution, often referred to as lambda cold dark matter, describes a universe in which structure forms hierarchically. Small dark matter halos collapse first. These halos merge over time to create progressively larger structures. Gas falls into these gravitational wells, cools, and forms stars. Over billions of years, dwarf galaxies merge to form spirals and ellipticals. It is a bottom-up process. James Webb began revealing what looked like top-down maturity. Several early galaxy candidates exhibited stellar mass estimates reaching billions of solar masses at redshifts above 10. At such epoch, the universe was less than 500 million years old. To reach that level of mass, galaxies would have needed to convert gas into stars at astonishing efficiency, perhaps at rates far exceeding those observed in later cosmic history. Initially, caution prevailed. Photometric redshifts can sometimes overestimate distances. Dust can redden light and mimic the signature of extreme redshift. Astronomers waited for spectroscopic confirmation, which provides precise redshift measurements by identifying emission lines such as Lyman alpha or oxygen lines shifted into the infrared. As spectroscopic data accumulated, some candidates were indeed revised to slightly lower redshifts, but not all of them. A subset of early galaxies remained firmly anchored in the epoch of cosmic dawn. Even after corrections, the tension persisted. These galaxies were massive, bright, and unexpectedly evolved. To understand why this is troubling, one must consider the timeline of structure formation predicted by simulations. In large cosmological simulations, dark matter halos grow gradually through accretion and mergers. The rate at which halos accumulate mass depends on the underlying density fluctuation seated in the early universe and on the nature of dark matter itself. The cosmic microwave background provides a snapshot of these primordial fluctuations when the universe was only 380,000 years old. Tiny temperature variations correspond to density perturbations that would later grow into galaxies and clusters. The amplitude and distribution of these fluctuations are measured with exquisite precision. From them, cosmologists derive predictions for how quickly structure should grow. If Webb's early galaxies are as massive as they appear, then either star formation within early halos was extraordinarily efficient, or the halos themselves grew faster than predicted. Both possibilities have profound implications. Star formation efficiency depends on complex baryonic physics. Gas must cool, fragment, and collapse under gravity. Supernova explosions inject energy back into the surrounding medium, potentially suppressing further star formation. Radiation from massive stars can ionize gas and regulate collapse. The interplay of these processes is intricate and often modeled using approximations in simulations. One possible explanation for Webb's findings is that early galaxies experience bursts of star formation far more intense than previously assumed. In the dense, pristine environment of the early universe, gas clouds may have collapsed rapidly, forming massive stars in large numbers. If feedback mechanisms were less effective at halting this process than models suggest, then stellar mass could accumulate quickly. Another possibility involves the initial mass function of early stars. If the first generations of stars were systematically more massive than stars forming today, They would burn brighter and shorter. Massive stars produce large amounts of ultraviolet radiation and heavy elements in a short time. Their deaths as supernova could enrich surrounding gas, enabling subsequent star formation to proceed efficiently. A top, heavy initial mass function could help explain rapid luminosity buildup. However, these adjustments have limits. There is only so much gas available in a given dark matter halo. The rate at which halos merge and grow is constrained by the cosmological parameters derived from the cosmic microwave background. If observations continue to reveal a high abundance of massive galaxies at extreme redshift, then deeper theoretical revisions may be required. One area of investigation involves the nature of dark matter. In the standard picture, dark matter is cold, meaning its particles move slowly compared to the speed of light. Cold dark matter allows small-scale structures to form early and merge hierarchically. Alternative models, such as warm dark matter, suppress small-scale structure formation and would generally make early galaxy formation even more difficult. Thus, if anything, Webb's results strengthen the case for cold dark matter, but they also test its detailed predictions. There is also the possibility that we are underestimating the uncertainties in stellar population models. Translating infrared luminosity into stellar mass requires assumptions about star formation histories, metallicity, and dust content. Early galaxies likely have lower metallicities than present-day systems, which affects how their stars emit light. Small changes in these assumptions can shift mass estimates significantly. Yet even with conservative modeling, the existence of surprisingly bright, early galaxies suggests that the universe was not quietly assembling tiny building blocks in isolation. It was rapidly organizing matter into luminous structures. Morphology adds another layer of intrigue. Some high redshift galaxies observed by Webb appear surprisingly compact and structured, while resolution limits prevent detailed classification. Hints of disk-like organization have been reported. If confirmed, this would imply that rotationally supported systems formed earlier than anticipated. In the local universe, spiral galaxies like the Milky Way exhibit well-defined disks and spiral arms shaped by angular momentum and gravitational dynamics. Forming such ordered systems requires time. Gas must settle into rotational equilibrium within a halo's gravitational potential. The presence of organized structures in very early galaxies suggests that angular momentum distribution and gas dynamics may have stabilized rapidly. Perhaps even more striking is the growing catalog of early quasars and active galactic nuclei. A quasar is powered by a supermassive black hole accreting matter at high rates. The gravitational energy released during accretion can outshine entire galaxies. Prior to Webb, quasars had already been detected at redshifts above 7, implying black holes with masses of hundreds of millions or even billions of solar masses less than a billion years after the Big Bang. James Webb now enables deeper searches for the progenitors of these black holes. If massive black holes are common in early galaxies, then the question of their origin becomes urgent. Black holes form from the collapse of massive stars, but stellar remnants typically begin with only a few tens of solar masses. Growing to billions of solar masses requires sustained, near-Eddington accretion or alternative formation channels, such as direct collapse of massive gas clouds. The existence of massive black holes in small, early galaxies complicates simple growth scenarios. Either seed black holes formed with much larger initial masses than previously assumed, or accretion proceeded at rates that challenge our understanding of feedback and radiation pressure. All of these tensions converge on a single realization: the early universe may have been more efficient at generating complexity than our models anticipated. It is essential to emphasize that none of these findings overturn the Big Bang framework. The expansion of the universe, the existence of the cosmic microwave background, and the large-scale distribution of galaxies remain consistent with established cosmology. The challenge lies in the details of how quickly and how efficiently structure emerged. As Webb continues to observe new deep fields, astronomers are building larger statistical samples of high, redshift galaxies. The goal is to determine whether the earliest massive systems are rare anomalies or common features of the young cosmos. If they are rare, then they may represent extreme but permissible outcomes within the standard model. If they are common, then theoretical recalibration becomes unavoidable. The terrifying aspect of these discoveries is not that they reveal chaos. On the contrary, they reveal order appearing too soon. They suggest that gravity, gas dynamics, and radiation combine to build galaxies with startling speed. They compress the timeline between darkness and structure. In a universe only a few 100 million years old, stars were already forging heavy elements. Galaxies were already shining brightly. Black holes were already growing. For centuries, humanity believed the early universe was a simple place, a blank canvas slowly painted by time. James Webb's gaze suggests that the painting began almost immediately, with bold strokes and rapid development. The deeper we look, the closer we approach the boundary between physics we understand and physics we are still struggling to describe. The galaxies that should not exist are not violations of natural law. They are invitations to refine it. As more data arrives, models will evolve. Simulations will be recalibrated. Assumptions about star formation efficiency, feedback, and early black hole growth will be tested against observation. The scientific method thrives in such moments of tension. Yet one fact remains undeniable. When James Webb looked too deep into space, it did not find a quiet, slowly maturing cosmos. It found a universe that may have grown up faster than we ever expected, assembling luminous, massive structures in the first breath of cosmic history.